Hello everyone, welcome back to Bytes of CAC. So in this lecture, we will be learning about the convolution neural network. Now, since this is quite an extensive topic, I will be dividing this into 6 different lectures, and this is the first part of your lecture. So in this lecture, we'll be talking about why do we need CNN. We already have MLP, which I have discussed in my previous videos. Now, why do we need this special set of neural network? And we will also be mathematically transitioning from a multi-layered perceptron to a CNN. Now, since you have shown interest in this lecture, I can safely assume that you already know that CNN deals with image kind of data. So we'll start with an MLP. Now let's look at what is generally the kind of data MLP deals with. So MLP deals with this kind of a data. So this is a regression problem. This is the Boston housing data set, and so a very important factor which I'll be discussing now, that see in this MLP what we do is we take the entire input and we fit that to a two-dimensional matrix where each row corresponds to one example and each column corresponds to a feature. And now we do the processing, and finally the output layer is going to produce some output. In this case, there will be just one output layer, so we don't need this anyways. So now suppose you just swap this age and tax column. So in one previous training, you used this was the order of the input features, and now when you're training it for a second time, you have just interchanged these two columns. So tax now comes here and age column goes here. Now, is it going to change the output? Like if you keep every parameter same, so what will it be? Like the output will always be the same. So from here we can say that MLP does not assume how features interact. Now there is some sort of an interaction between the features which will give a particular value of the target. So it does not assume a priori, rather as it goes through the training process, it tries to find out how the features are interacting among themselves. So this is a very important what shall I say, characteristic you should remember about MLP. This will be needed while we are discussing the convolution neural network. Now let's move on to image data. Suppose I have the Google image logo. Suppose this is a very low quality picture and I start zooming in, and after some time the image or the logo looks like this. So if you look at this picture closely, you will find these small, squares, and these squares are known as pixels. And what are actually pixels? So pixels contain a part of the entire image. So this is actually a picture within a picture. And when we are talking about the Boston data, like we are talking about the typical MLP data, the example we were discussing about. So there are different features like the age of the house, the tax to be paid, and bedrooms, and so on. But when we are dealing with image data, what is that feature which is to be input? Now see, when these pixels are arranged in a particular way, in this case in a two-dimensional plane, it reveals the entire image to you. So therefore, in this case, or in case of image data, the pixels are the features of the image data. So typically what we do is the information contained within each pixel is converted to some numeric value, and that is fed into the neural network. So suppose your image is of 1 megapixel, which is pretty low quality image in today's standard, because I'm sure even the front camera of your phone, your smartphone has a better, I mean, it gives a better megapixel image than 1 megapixel. It is more than that, right? So 1 megapixel means there are actually 10 to the power 6 total pixels, where 10 cube are uh, like arranged along the x-axis and 10 cube along the y-axis. So for a 1 megapixel image, the number of input features will be 10 to the power 6. This is how it is calculated, or this is how it is worked with. Now, let us look into how we actually, as human user, how we actually uh, do image classification, because in case of CNN you will mostly be doing image classification, right? So I think you have come across this image too. Now when you do those when you browse those websites, sometimes the websites just try to make sure that you are not a bot but a human user, and they ask you to just click on each image containing a car. So how do you actually accomplish this task? So what you typically do is you will actually look for the car, and you will only look for that if there is a car in the image. Now if you don't agree with what I'm saying, let's take another example. Suppose I give you a picture and I ask you that, do you see Simon in the picture? And like most probably you don't know how or who Simon is. So the question, just try to map that. The question you'll be asking is, how does Simon look like, or how does Simon look? Because you know that it does not matter like where Simon is, that is the location of Simon does not matter, because Simon can be anywhere. It is not that the Simon will always sit at home or Simon will always be at work. Simon can be like, he can be anywhere. So the background of the Simon can always change. But the features of Simon will always be the same if we are considering a recent photograph, or if I show you a recent photograph of Simon, the features of Simon will always be the same. Maybe Simon will be wearing a different dress, or maybe he'll have a different haircut, or even a hair color, but the eyes of Simon, nose of Simon, those will be the same. And we are not considering the plastic surgery case, so please. Okay, so now I show you this is how Simon looks like. And now you just try to map each of the, what shall I say, cartoons present in this picture, and you try to find out that if that is Simon. So you compare this to this and you say that no, this is not Simon. But when you compare this to this, you say that probably this is Simon, and you tell me that yes, I can see Simon in the picture. So why am I actually saying a whole lot of story here? Because this story contains two very important features of an image, or two very important characteristics of an image. First is the translation invariance, which means the neural network should respond similarly to the same patch regardless of where it appears in the image. Like, this is the part of the story. Now see, here, if you consider the background of this image, here the background of Simon is in yellow, while here the background of Simon is green, because Simon is standing probably in a park or maybe in a garden. I don't know. Anyways, so regardless of whatever be in the background or whatever be in the vicinity of this particular patch, your network should always like when it compares this patch to this patch, the result should always be the same. And another is the locality principle. Like in normal case, it is not possible that the legs of Simon is here and then the head of Simon is hanging like a fruit from this tree, and so on. Simon will be present at one particular patch of this image. And yes, we are not considering the case of a murdered, mutilated Simon, right? We are just considering a normal case. So in a normal case, you will always find Simon in a in a local what shall I say, patch of this image. Simon will be present. Okay. Now these two, please remember these two characteristics, because these will be needed when we are framing the equation for the convolution neural network. Now let us move on to that part. So let us consider that xij is a pixel at location ij for the input image, and hij is a hidden representation for the pixel at location ij. Now this is a two-dimensional data, because this is every pixel has a particular location information too. So in order to make sure that each of the hidden units receive input from each of the input pixels, a fourth order weight tensor is used here. Now the question is, what is a tensor? So in very simple words, tensor is just a n-dimensional array with n indices. So when this is one dimensional, we call that a vector. When it is two dimensional, we call that a matrix. And for tensors higher than 2 dimensions, we just call it a n dimensional tensor or a nth order tensor. So your fourth order weight tensor means there will be 4 dimensions. Now we start with the MLP equation, where in order to find a hidden dimension, you will just multiply weight with the input and you will add the biased weight. So here, since we are considering the location information too, so your bias will also be a 2-dimensional tensor. And now we sum over K and we sum over L. This is the two dimensions of your data, or 2 dimension of your input data. And what this double summation is doing here is a cross correlation. So if I have to explain that using a program, it is basically a nested for loop. Suppose x has 5 indices, your y has 4 indices, and now you initialize your sum. This is your sum. You initialize your sum to 0. So first you will run the k in a for loop in the range of x. This is a Python program basically. Since Python is very easy to code, I've just used Python because it's, the number of lines of codes are really small in this, less in this case. And for L in the range of y, we compute the sum equals to sum plus k into L. And finally, the value of sum is this. Now, if you want to have a better idea of how this double summation works, I will put a link to an YouTube video, which I think is very succinctly put, and that will be given in the description box. Please go through that video if you are still confused with what a double summation is actually doing. Now here, I'm not going to explain that in this lecture because it's going to make it too long. So, so now here, we will be making some changes. Like we will be substituting k to I plus a, and then we will be substituting L to j plus b. So we are just re-indexing the subsets. And we will be setting this ijk, so this is actually k and this is actually L. So we will be setting this to Vijab. So this is substituted by this. And now your equation looks like this, right? So this this indices A and B will run over both the positive and negative offsets. So basically for a particular ij, for a particular value of ij, it will cover the entire image. So we are actually using this translation. So it will move up, down, sideways, and it will cover the entire image, and that value, like the hidden dimension now, like the calculation of the hidden dimension now works in this fashion. And there's a reason why we are doing this. So till now, say we are considering a 1 megapixel image. So this is going to have 10 to the power 6 parameters, and there are 10 to the power 6 hidden dimensions too. So this is also 10 to the power 6. So the number of parameters needed in this case will be 10 to the power 12. I mean, that is a lot of parameters. And for training a neural network, I mean, it will take days to actually train this neural network. And just get it very clear, training the neural network once will not produce a very good model. You will have to train it a number of times using different hyperparameter tuning and so on. And you will be needing lots of GPUs. Like, it is a very computation heavy equation, and well, it is really not worth it, because what a human classifier can do in seconds, you will just need months to actually train the model to to do this basic classification task. Now, where are we actually stuck? I mean, why is it taking so many parameters? The number one thing is, as I said, MLP does not assume that features have some relationships among each other, whereas in case of image data, the features do have relationship among each other. The location of the pixels and the adjoining pixels, like the pixels in its vicinity, it does interact in some way. So now we are trying to incorporate that information. So the first feature was translation invariance, which now we will be incorporating here, which assumes that, or which says that a shift in input X should simply lead to a shift in the hidden dimension H. So now this can only be possible if V and U, they do not depend upon the location. If this is not location independent, then only we can incorporate this translation invariance. Now what we do is we change this fourth dimensional weight tensor to a two-dimensional weight. So now this becomes this, and your equation now looks like this. So U in this case, since it is not location dependent anymore, this is a scalar quantity now. Now your image, in this equation, you are still actually covering this I plus A and J plus B, this factor. This is actually still covering the entire image. So number of parameters needed in this case is 4 into 10 to the power 6. 10 to the power 6 because, as I said, it is covering the entire image. Now we consider the second characteristic of the image, which is locality. And locality says that in order to garner important information or specific information in your image, you do not have to actually look very far. You can just do that. I mean, you can just move within a range and you can get some important information regarding the patch of image. So for now, instead of scanning the entire image, that is minus 1000 to plus 1000, like A and B, which was moving around this, you know, it was moving from minus 1000 to 1000 in this 10 to the power, like in this 1 megapixel image. We say that now A and B should move, like should look within the range minus delta to plus delta, and this delta value is typically less than 10, you know. And now when you rewrite your equation, it looks like this. So now A is from minus delta to plus delta, and B is also from minus delta to plus delta. And this value of VAB for ranges beyond minus delta and delta is going to be 0. So now this is what you call a convolution layer. So this is a convolution layer, and this V is known as a convolution kernel or a filter. And yes, in this case, since this was 4 into 10 to the power 6, the number of parameters in this case, so in this case the number of parameters becomes 4 into delta square, and since delta is typically less than 10, the number of parameters are quite, it is computable. It is far computable. So we shifted from 10 to the power 12 to 4 into delta square, right? So now the question is, why do we actually call it a convolution neural network? What is this convolution? So suppose we have two functions f and g, which takes on a one-dimensional, like it takes on some vector value. So the convolution between these two functions are shown like this. So what we do is we multiply fz with g, where g is flipped and then shifted by x. And now suppose the objects are discrete in this case. This integral turns to a sum, and this is what we get. And now suppose instead of vector we are considering two-dimensional tensors, we will have the corresponding sum with indices a, b for f, and I minus a and j minus b for g. So you have double summation, since there are two dimensions to this tensor now along a and b. So now this somewhat looks like this. If you just disregard this u plus part, like if you just disregard the bias, these two almost look similar, with just a minor difference, like this was I minus a, j minus b, instead you have I plus a and j plus b. Now this is not quite a big difference because this is mostly cosmetic. So this is why we call it a convolution neural network. This is because of the similarity of these two equations. So okay, so that is all for today, and please stay tuned for the next parts. So thank you for watching.